Hi everybody, my name is Groysman and I'm a professor of inorganic chemistry at Wayne State University. My group research involves design of organometallic catalysts that use organoazides as precursors. And so the goal of this presentation is to discuss safe handling and safe chemistry with organoazides. This presentation was prepared by me and Dulika Vanipurage, a former graduate student in my group. So organoazide is a very common functional group in organic chemistry that looks like that. It's quite common in catalysis for a number of reasons. It's generally quite easy to synthesize. It can lead to many useful nitrogen-containing products. It's also considered to be environmentally friendly reagent, as the only byproduct of its reactivity is dinitrogen. However, organoazides can also be potentially explosive and can lead to very serious lab accidents if not handled safely. And so our goal today is to talk to you about the dangers of organoazides and about safe ways of doing chemistry with organoazides. Before we actually discuss which organoazides are particularly dangerous and how they should be handled, let me give you some recent examples of explosions caused by organoazides. One such explosion happened at the University of Minnesota. Here, the student was distilling a very large quantity of particularly dangerous trimethylsilyl azide. It is possible that it also was contaminated by hydrozoic acids, which is shock sensitive. You can see the effect of explosion on the hood here. Fortunately, the student was carrying out the reaction behind a safety shield, which absorbed most of the impact, yet the student did suffer significant injuries. Another explosion with organoazide happened at the University of Akron. Here the student was preparing an organic azide by using sodium azide precursor. In this case, the reaction was not carried out safely, and the student was not wearing safety attire properly. However, thanks to the closed hood sash, the injuries that the student suffered were not severe. The azides can be dangerous. However, not all organic azides are equally dangerous. There are some simple rules that can help you to identify azides that are particularly dangerous. So there's a very simple equation, you can see it here, that can tell you that the azide in question is particularly unstable. The idea is that for the azide to be stable, the C/N ratio should be 3 or above. Yet even organic azides with C/N ratio below this number can be handled, but with the proper care. They generally should be prepared in small quantities and preferably stored as dilute solutions. The magic number that should not be crossed is 1 to 1. So organoazides with a C/N ratio of 1 or below should preferably not be used. If you must use them, it has to be done on a very small scale and with a lot of caution. This point is generally demonstrated well with alkyl azides. Just as an example, nonyl azide, which has the C/N ratio of 3 to 1, should be the smallest azide isolated. However, octyl azide, with C/N ratio slightly below that, is quite similar in its stability to the nonyl azide and can be handled with care. However, methyl azide or ethyl azide, with C/N ratios below 1 to 1, are shock sensitive, can explode around room temperature, and should not be isolated in a pure form. So the rule of 6 is a good approximation to the stability of organoazide. Basically, you need to have at least 6 carbon atoms per each azide group. Okay, so we have the rules which tell us which azides are particularly dangerous. Does it mean that we can treat the rest without care? No. Generally, even if the azide is predicted to be stable, it still should be treated as a potentially explosive compound. Of course, you always need to have the proper safety attire, which include safety goggles, lab coat, and appropriate gloves. It's a good idea to handle azides, particularly dangerous ones, behind a blast shield. And it's not always possible to prevent accidents. We always want to prevent accidents. However, accidents can happen, so never work alone in the lab. If an accident happens, someone needs to be in the vicinity to call for help. It is generally a good idea to store organoazides cold in the absence of factors which can cause explosion, light, heat, or shock. Organoazides should also be stored separately from other chemicals. They should be disposed of in a separate container. As with many other explosive chemicals, their concentration under vacuum may lead to explosion and should be avoided or carried out in a particularly careful manner. This presentation talks specifically about organoazides. However, we should also mention here metal azides. Metal azides, such as sodium azide, are frequently used as precursors for organoazides, and handling of metal azides requires some additional precaution. So metal azides are often shock sensitive. In addition, they're quite toxic or can lead to very volatile and toxic compounds. It is generally a good idea to think about compatibility of your metal azide with other reagents, including solvents. For example, do not use chlorinated solvents when you're using metal azides. Both chloroform and methylene chloride can form diazide or triazide methanes, which clearly are explosives. So upon reaction with acids, metal azides can also form hydrozoic acid NH3, which is highly toxic, explosive, and low boiling. Given all of the above, it's always a good idea to write a standard operating procedure, SOP, before carrying out a reaction in which an azide is used or produced. So this SOP should be based on a specific MSDS of your specific azide, also on the considerations presented above. After writing this SOP, always discuss it with your advisor, and also remember that any chemical needs to be stored and disposed of at some point, so try to order or create smallest amount possible. Now let me go over some of the laboratory procedures which should be used when working with organoazides. Again, azides are potentially shock sensitive. It's not a good idea to remove them using rotary evaporators. If must, better to use simple vacuum and of course do it behind a blast shield. Let's mention the blast shield again. Dulika can show you how to do that. Here is the reaction carried out behind the blast shield. And of course, to use an additional level of protection, bring the sash down as much as you can. You can also see it here. Again, reaction carried out behind the blast shield, behind the sash. When you add metal azide to your reaction in the synthesis of organoazide, do it cold and never add the reagent fast. Add slowly using either a dish and funnel or a pipette, and always look for any signs of exothermic reaction. Now Dulika can show you how to do that. If you need to carry out an extraction using a separatory funnel, do not shake too vigorously. Again, these things can be shock sensitive. Dulika will show you here how to do that. So here you can find some additional useful resources to check out prior to working with organoazides. Take a look at these publications as well. And we would like to wish you safe chemistry with organoazides, and thank you for your attention.